you know who to contact. Okay, so I'm Florin Constantin. I work at the subsidiary of Amazon next to Stanford University. This is what A9 is. And this is work I've done while I was a postdoc at Georgia Tech. And Ruta Mekta, the main author, was visiting my postdoc host, Nina Balkan. And in this work, we highlight the lack of robustness of one of the most prominent connections between learning theory and game theory. And let me offer you a one-slide summary of our result, and then I'll go over everything in more detail. So all the three orange results that you see are for computation of Nash equilibrium in two-person games, finite games. The left two orange results are fundamental results in game theory. The first one is for computation of Nash equilibrium that's simultaneous for both players at a time. So for zero-sum games, one can write a linear program that computes a Nash equilibrium. So there's a polynomial time algorithm for computing a Nash equilibrium. The bottom result shows that in zero-sum games, weighted majority, the averages of weighted majority, converge to a Nash equilibrium in zero-sum games. This is a result to Freund and Shapiro. Now, the top left result, the one by Danzig, was extended in a recent paper by Ruta and co-authors to a superclass of zero-sum games called nearly zero-sum games that I'm going to define when needed. So a natural question, as you can see, there's a gap in there. Natural question is, does convergence of weighted majority extend from zero-sum games to nearly zero-sum games? And our contribution is to say that, well, it doesn't converge. So don't worry about the details of the graph. The graph shows something that diverges. And there are longer and longer epochs. That's what I want you to remember for now. And the way we show this result, so that the answer is no, we characterize the dynamics of weighted majority in a subset of this nearly zero-sum game class. And we do this for any initial conditions. Okay, so this is the one-slide summary, and now let me go over everything in detail. So let's start with biometrics games, which are games with two players, a number of actions, and simultaneous moves, where players move simultaneously. So for example, rock, paper, scissors. And we're going to have a row player and a column player, as is customary. So let's say that the row player plays paper and the column player plays rock. Well, since paper covers rock, paper beats rock. So the row player gets a payoff of 1, and the column player gets a payoff of -1. So row wins, column loses. And we can split this payoff matrix into the row payoff matrix capital R. So the first italic entry in each column, in each cell, and the column payoff matrix, which is the second entry. And in particular, rock, paper, scissors is a zero-sum game because the entries in each cell add up to 0. So a central question in game theory is finding Nash equilibria. So Nash equilibria are states or pairs of actions or strategies, some that may be mixed, where players best respond to each other. And it's well known that for rock, paper, scissors, the only Nash equilibrium is one where each player plays each strategy with equal probability. So if I equally randomize rock, paper, scissors, there's nothing that the opponent can do to get more than 0 payoff in expectation. So a lot of this talk is concerned with how to compute Nash equilibrium and whether weighted majority works for that in nearly zero-sum games. So let's start with the centralized when it's one algorithm for both players. So even for biometrics games, this is known to be PPAD hard, which is widely regarded as intractable. But when we restrict from general biometrics games to zero-sum biometrics games, then there's a linear program, as I said, so that's tractable. How about independent learning? So where each player uses an independent algorithm, and then they somehow reach an equilibrium. So in a standard model, there's an infinitely repeated play of this game. So we play rock, paper, scissors today, tomorrow, day after tomorrow, and so on. And at any such time step t, like a day, I'm going to denote the row player strategy by RT. and the probability that the role player is going to play action I is going to be RIT, fairly standard notation. And similarly for the column player, CT is going to be his mixed strategy, and I'm going to similarly denote the probability of action J. So for example, if the player was playing 1/3, 1/3 uniformly, each RIT would be 1/3. So once we have this individual, this step strategies, we wonder about convergence. So we distinguish between two types of convergence. The first one is convergence in strategy, where the sequences RT and CT converge to an individual strategy, R or C. The second type of convergence that we're concerned with is a less restrictive one. Its convergence is an empirical average, where the average over time of strategies converge. So when thinking about learning in multi-agent settings, it matters to look at the type of information that, say, the role player knows about the column player. And we focus here, so we prove our negative result in the most powerful model, where the row's strategy, next strategy RT plus 1, may depend on the column player current strategy CT. So let's see one type of learning algorithm that you're probably quite familiar with. So it's called the weighted majority learning algorithm, and also goes by a few other names. And this is a learning algorithm for learning algorithm from expert advice that exhibits vanishing regret. And when applied to games, each action corresponds to one expert. So there's a one-to-one mapping between action and experts. And good, as in the regular weighted majority, good actions at time t are encouraged. So let me explain the first equation, how the probability of the role player at the next time period t plus 1 playing action I depends on the current probability. So the next probability is proportional to the current probability times the learning rate, say E, to an exponent that's essentially the expected payoff of action I that the role player gets, given that the column player draws, plays the mixed strategy CT. So it's just the ith row of the row payoff matrix times CT, which is a probability distribution. And similarly for the column player. So it's known that weighted majority converges in empirical average to Nash equilibrium, converges in zero-sum games, which is a classical result of Freud and Shapiri, and also in potential games, which is a more recent result. And there's another type, there are of course many learning algorithms. A prominent one in game theory is called fictitious play, which is known to converge in strategy, so the stronger type of convergence, to Nash equilibrium for zero-sum games, potential games, and a few other classes of games. So given the old and well-established results for zero-sum games, it's natural to consider, well, how robust are these results? How far can they be extended beyond the class of zero-sum games? And to quantify this expansion, I'm going to use the rank of the